Welcome back to our little series on Vertex Operator Algebras. This is episode 9. Today we are talking groups. Physicists are probably more familiar with group representations, and today we will bring those into the conversation. But we are going bigger than that. To embed them into the flow of our normal conversation on algebras, we'll need to construct a curious hybrid beast, the group algebra. Let's get started. You might recall how we've stressed over and over again that a vector space can be thought of as a field action on an abelian group. In that discussion, we thought of the basis vectors as being members of that group. That group operation, which is abelian, so we often call it plus, cooperates with field addition. And of course, field multiplication is extended to distribute across the group addition. Today, we're going to have a different spin on that idea, although the constructions will be unrelated. Note that we're not defining a unique or fundamental construction here. We're modeling certain mathematical behavior with ideas. These are descriptive conversations. We're trying to be precise as possible, sure, but there's no real morally correct way to describe them. Ultimately, you can always go back to the axioms and build up the formalism from the ground up. Victor Kaas's book, linked in the show notes, is a reasonable place to start if that's what you're into. Okay, group algebras. Let's start with the big beastie first. Let G be some group, which need not be abelian. Let f of G be the vector space of finite linear combinations of elements of G over the field f. F of G has the obvious algebra structure with vector multiplication provided by the group operation. Okay, so 2 comments. First, for this construction, we are relying on vector addition as a formal sum of elements of G, but unlike our previous construction, we are not identifying addition with this group operation. Indeed, the group operation may not be commutative. This is a different, albeit similar construction. The former was a generic way to represent any vector space. This is a specific construction for a particular sort of algebra. Second, the group operation is necessarily associative and has a unit. And because we're using the group operation to model vector multiplication, f of G is necessarily an associative algebra. Okay, great. Now, let's discuss group representations. Like algebras, groups too can have a representation. Let V be a vector space. A group homomorphism from G into the automorphisms of V is called a representation when 2 conditions are met. First, the automorphism associated to the unit element of the group must be the identity. Second, products of elements map to sequential left action. V, in this case, is called a G module. Similar to the algebra representations and modules upon which they act, the group versions can be irreducible, indecomposable, and trivial. Here, a trivial group representation maps the action of the entire group to the identity automorphism. Remember how trivial modules for algebras mapped everything to a 0-dimensional vector space? We are already seeing some subtle differences between group and algebra representations, and we will encounter these in greater detail later on. Tensor products. Finite tensor products of group modules are also group modules, where the group action acts on the product by acting on each factor simultaneously. Notice the distinction here between algebra actions and group actions. Namely, group actions are not linear. Group algebra modules. Here's an important fact. G has a natural representation on f of G. This is the so-called left regular representation, which, unsurprisingly, acts by left group multiplication. Any G module can become an f of G module, and indeed they're basically the same thing. Assuming, of course, that the underlying field of the G module is the same which we use to construct f of G. Abelian groups. A bit of caution is in order. There's a potential for confusion if G is an abelian group, whose operation is traditionally written as addition. In this case, we will have trouble distinguishing between the group operation, which is vector multiplication in the algebra, and vector addition. In other words, our notational models are colliding, and we have to be clear on what we're talking about to move forward. In this case, we change notation and write the elements of G in f of G using an exponential. So that f of G for abelian G is now linear combinations of elements that look like e to the G. Lest you worry that this is starting to get baroque, this notational change will actually make contact with precise definitions later. In other words, any emotional reaction to the notation at this point can be considered as a quirk of the way the material is being presented. Remember, this is all still background material. Now let's discuss induced modules of these beasts, and let the analogies continue. Suppose H is a subgroup of G. Evidently, f of H is a subalgebra of f of G. Let V be an H module, which can also be thought of as an f of H module since V and f of H share the same underlying field. We can construct the f of G module induced by the f of H module V, which we will call the induced G module. As with our discussion from section 8, f of G is an associative algebra, which affords a canonical inclusion map from V, 1 times V, which can be used to define a universal mapping property. Just a quick remark that the authors make about the structure of this induced module. If X is a subset of G which contains exactly one element from each left coset GH for each G and G, then the ideal used to construct the induced modules on the span of X is basically trivial. Put differently, we can model the induced module as a simple tensor product of the linear span of X with V. In other words, X represents the orbits of elements of G by right action by H. Okay, let's have a look back on what we did today. We found a way to relate groups and associative algebras through their representations. The connections between groups and algebras runs very deep, especially in Lie theory. Lie algebras can be associated with a certain kind of group, so-called Lie groups. A Lie group is something like a differential or continuous group, and a Lie algebra is kind of like the tangent space to such a group, an infinitesimal version of the group transformation. We need something that can serve as the f of G analog for this Lie group. This analog is the universal enveloping algebra that we are building towards, and we will see in section 11. Alright, and that's our show. Next time, let's discuss tensor algebras.